Greetings. My name is V.M. Bala Balasubramaniam. I am the professor of food engineering at the Ohio State University. In this presentation, I would like to share some of the applications of high pressure based technologies for beverages. Particularly, we will be looking at inactivation of bacterial spores and vegetative cells through application of pressure treatment. This presentation is part of the Symposium S4 Recent Advances in Beverage Processing Considerations and Outcomes. And before we get started, I would like to thank the symposium organizers and IFP for having me as a part of this symposium. So today, consumers are interested in variety of things from beverages. In addition to quenching thirst, they seek consumers which are healthier and made from natural products. They like to have more protein drinks, and consumers like to reduce the sugar intake, and they are interested in clean label, all natural products so that the beverages contain no synthetic preservatives, artificial flavors, or sweetness. Finally, in addition to all these things, they want to make sure that the beverages are microbiologically safe, and that's always important. So one of the technical solution that may enable this possible is the high pressure based technologies. Um, Basically, the technology utilize application of elevated pressures, 400 to 600 megapascal, with or without moderate heat addition. If you're not familiar with the term megapascal, 400 to 600 megapascal is about 87,000 pounds per square inch, or approximately equivalent to going about 25 miles at the bottom of the ocean and keep it for a certain time before reaching the surface. The like thermoprocessing, it is a versatile technology which is applicable for both liquid and solid foods. It's possible to have both batch and continuous pressure treatment. Today, you primarily see the application of batch processing methods, but research is going on in universities, including at the Ohio State University, develop continuous pressure treatment. In general, pressure accelerate the microbial inactivation, and with that, you can able to achieve pasteurization, typically 400 to 600 megapascal pressure treatment at chilled or ambient temperatures for a couple of minutes, and it's kind of common industrial practice now. It's also possible to commercially sterilize, make a self-stable beverages with the pressure treatment in combination with the heat. And FDA issued letter of no objection to two industrial petitions for PATP. However, it's not a commercial practice yet. So, as I mentioned, the food pasteurization applications, it is widely commercially practiced. Continuous method process for high pressure processing is in research phase, including the research being done at Ohio State and elsewhere. So if you look at the pressure thermal treatment, different combination of pressure thermal treatments intensities can result in different treatment effects. So for example, when you have pasteurization, typically involves pressure treatment at ambient or chill conditions, inactivate most of the vegetative pathogens, foliage bacteria. However, the spore-forming bacteria are not inactivated, and enzymes have variable efficacy with this treatment. With combining pressure and heat, 90 to 120 Celsius, can able to achieve inactivation of bacterial spores as well as the vegetative bacteria and enzymes. The process is called pressure-assisted thermal sterilization, And this is more intensive form of treatment that utilizes both pressure and heat. However, um, this is not a commercially um, practiced. FDA issued letter of no objection for two industrial petitions. Between pasteurization, which is a milder form of a milder form of pressure treatment, and PATP, which is a more severe form of pressure thermal treatment, you can also have what we call extended shelf life ESL products, where you can combine pressure with moderate heat, 60 to 90 C, so that you can inactivate vegetative bacteria, and you can also inactivate some of the psychotropic non-proteolytic Clostridium botulinum, and the spores of the proteolytic Clostridium botulinum may not be inactivated. It's also worth note that the ESL as well as PATP, more research is going on, and in terms of identifying the kinetic destruction of various spore formers. In terms of equipment, high pressure processing primarily practiced as a batch systems. The equipment can be a vertical orientation or horizontal orientation shown here. So for example, the equipment typically consists of a pressure chamber kind of housed behind this panel, and you could have a conveyor mechanism which can feed in the carrier basket containing the product. The product is packaged in a flexible container or plastic bottles, and then load inside your pressure vessel through a conveyor mechanism, and then the product is processed at a specific pressure, temperature for specific hold time, and then the processed product comes out in the other side of the vessel and then taken out. High pressure pasteurization today is one of the fast industrially adapting technology. In the USA and globally, it's a $14 billion market. And among the high pressure processed product, which include categories including seafood, ready to eat meats, fruits and vegetable products, dairy, and juices and beverages, the beverages is about 24% or almost one fourth of the high pressure pasteurization market segment. You have variety of fruit juices and vegetable juices can be processed, smoothies, nut-based milk, like for example, almond milk, um, milk and yogurt, even though it is not commercially available in the US, it is kind of commercialized in the Australia, for example. You also have cold brew coffee, tea-based drinks, soups, kombucha, and various energy drinks are possible with this technology. These are just representative pictures of pressure-treated products. You can see that many of these products are fruit or vegetable-based drinks, which are high acid in nature. For example, it has a mango drink or like a variety of other fruits. You also have some of the vegetable-based low acid drinks like a carrot juice or coconut water is one of the very um, popular high pressure processed product. In addition to that, you can also have various dairy-based beverages, so yogurt, milk, and other type of products also available in the market. So when you are interested in developing a high pressure based technology, how are you going to validate this? First, you need to identify what is the most resistant pathogen of public health concern that likely to survive the process. And then you need to identify what level of inactivation is needed. Typically for pasteurization, depending on the food matrix, about 5 log, 6 log reduction is desired. Then you need to consider the injury and recovery of the bacteria. You also need to consider the impact of the food matrix on the pathogen survival, the influence of composition, pH, water activity, all needs to be considered. Finally, you need to validate the process efficacy. So, a typical high pressure pasteurization process or commercial sterilization process consists of um, monitoring both pressure history as well as the temperature history. So, for example, when you begin the process, you need to precondition the product at a certain initial temperature, and then you are ready to load inside the pressure vessel. Once you load it, you apply the pressure. The pressure is built up for a certain time. This time is the compression time, or it's also called the pressure come up time. And then it's hold at that condition for a certain time, which is called pressure holding time. Then the pressure is rapidly decompressed and depressurization time. It's also interesting to note that during the compression time or come up time, the product temperature increases to a certain value from your initial value to some final value, depending on the composition of the food matrix. So, for example, water has 3 degrees Celsius per 100 megapascal temperature increase at 25 degrees Celsius. Then the temperature may be maintained assuming the vessel is insulated. And then when you release the pressure, the temperature also return back to close to the initial value. So the process control parameters for this process include the target pressure, the initial temperature, process temperature under pressure, as well as the pressure holding time. You also need to consider the product specific parameters such as the pH or acidity of the product, water activity, formulation, and preservative and antimicrobial agents. Unlike thermoprocessing, during high pressure processing, it may be possible the spore population, for example, can be reduced certain value during come up time. Depending on the type of strain or bacteria, you may get no reduction or about a log reduction, or in some cases about 4 log reduction. So this is something you need to consider, particularly when you're going to consider doing some kinetic modeling type studies. The other thing is the different strains of the bacteria, even within the same bacteria, can exhibit wide range of resistance. A study was conducted to look at 100 different strains of Listeria monocytogenes, and they found the following. About 30 strains probably had about 3 log reduction, and then some strains probably did not have any reduction. On the other hand, maybe a couple of strains had about 6.75 log reduction. So if you're going to select the your strain based on this particular strain here, you may get quite significant inactivation. But if in your particular product have any bacteria from this group, you're going to likely to have an outbreak. If you choose the strain based on this data, you may have maybe a 50-50 chance getting an outbreak. On the other hand, if you're going to choose a strain here, you may probably decide high pressure processing never going to be working for me. So what you need to do, you probably need to look at the region where you are working from and kind of consider some of the outbreak strains in the food matrix in that region. And perhaps you may consider work with your process authority and have 3 to 5 different strain cocktail and conduct validation studies using your specific food matrix, and so that you can able to establish your process. While it's tempting to just to take a strain which is published in a literature, that may not be quite relevant to the type of work you may be doing in your particular product. So it's always important to look at your product and look at um, what are the potential target strains and able to conduct your own studies. Another thing you need to consider is the impact of temperature and pressure and the condition at which you get complete inactivation or inactivation without any injury. So, for example, in this study, again with the Listeria monocytogenes, where we were looking at 300 to 450 megapascal, 30 Celsius to 50 Celsius. If you are going to go in a very modest temperatures and pressures, say 300 to 337 megapascal, and range of temperatures here, you may primarily get black region, which is consists of dead bacteria and injured bacteria less than 5 logs. On the other hand, if you increase the intensity of the treatment, going up in temperature and pressure, so for 450 megapascal and certain temperatures, 50 Celsius, you get into the white region where you get more than 5 logs of dead bacteria. So you kind of wanted to achieve this region so that you probably don't want to have any injured bacteria in your treated sample. There has been wide range of studies have been conducted in different food matrices, like for example, grapefruit juice, um, aronia juice, pomegranate juice, carrot juice, and so on and so forth. And they kind of often provides the experimental parameters, target organisms, and the level of reductions, and so on. So you need to carefully assess the literature, and then it's better to do your own studies as well. Another thing is there has been only limited studies conducted so far on the inactivation of the spoilage organism under high pressure. So, for example, LAB strains, lactic acid bacteria, oftentimes one of the common spoilage organisms in the pressure treated foods. And we looked at the inactivation of LAB strains, different strains in pressure treatment at 600 megapascal, 10 degrees Celsius, and 25 degrees Celsius. And what we have noted is lactic acid fermentum and plantrum are among the easy to inactivate organisms under these conditions. On the other hand, lactic acid previs and acidilacti, they are relatively more pressure resistant under these conditions. So this is something you need to consider so that your product not only microbiologically safe and also relatively free from spoilage. Pressure assisted thermal processing involves combined application of pressure 400 to 600 megapascal with heat 90 to 120 Celsius so that you can inactivate some of the harmful bacterial spores, including proteolytic Clostridium botulinum. You inactivate the enzymes. This provides opportunity for a variety of low acid, self-stable beverages, stews, soups, tea, coffee, cream sauce, and so on. FDA issued no objection to two industrial petitions in the past several years. Mashed potato and seafood are example products. However, at the moment, there's no commercial product available in the market. If you have an acid product, you don't need to go up in temperature that much. You can able to reduce the temperature. These are called extended shelf life products, and they can inactivate the cyclotropic spores, non-proteolytic Clostridium spores. And depending on the food matrix, if it's a low acid food matrix, the proteolytic Clostridium botulinum may survive, and you can able to keep them ambient stable if it's an acid product. If it's a low acid product, you may keep them under refrigeration. So this way, the milder treatment condition may help to preserve the product quality and nutrition attributes. Number of the juices and beverages can fall into this category. So for example, you can able to create a self-stable tomato juice by moderate pressure temperature treatment. So for example, maybe 600 megapascal, 85 degrees C or 95 degrees C for about 2.5 minutes. On the other hand, if you go up to 105 degrees Celsius, you may have less than 30 seconds treatment may be needed to create a self-stable juice. It's important to understand the synergy between pressure and temperature. And there are regions where pressure play more synergistic with the heat. There are regions where temperature may become a dominant factor. To illustrate this point, we conducted a study where we looked at the integrated pressure thermal lethality. In the first set of experiments we have done at 600 megapascal, 103 Celsius, 5 minutes. The bottom line here, pink color, shows that thermal only lethal effect. And you can see that under these conditions for bacillus amyl liquefacions, the lethal effects are very less. On the other hand, when you combine pressure and temperature 600, 103 Celsius, you can see that there's a significant increase in accumulated lethality under these conditions. If we repeat this experiment at a higher temperature, 600 megapascal, 116 Celsius for 5 minutes, you can see that the thermal only lethal effect is now quite comparable compared to the combined pressure thermal lethal effect. And if you're going to repeat this experiment at 600 megapascal, 121 Celsius, and you will see that this pink line is going to shift and match this line, indicating that under these conditions, thermal only effect become dominant factor. Pressure has a less lethal contribution under these conditions. So this is something you need to consider when developing the process. In addition to that, the pressure and temperature can interact with each other in a synergistic way or antagonistic way. To illustrate this point, we have done this study with the M2 chemical marker, which is basically a whey protein gel. And to illustrate here, we have done studies with the whey gel um, at zero point 0.1 megapascal, 105 degrees Celsius. The marker yield significantly increased with increasing in thermal holding time, and the temperature is kind of quite high under these conditions. If we were to repeat this under room temperature 30 Celsius, under high pressure 350 megapascal and 700 megapascal, you can see that the temperature is 30 and pressure is a dominant factor, but pressure suppresses the formation of marker under these conditions. If we repeat the experiments at 105 degrees Celsius, 350 megapascal and 700 megapascal, particularly at 350 megapascal, you can see that the marker yield start increasing again with increasing in temperature. In other words, the temperature is kind of increasing the formation of marker, pressure is kind of suppressing the formation of marker, and the specific treatment condition, you're probably going to have an antagonistic effect. So this is something needs to be considered when you do high pressure treatment of various microbiological reactions or chemical reactions. In a recent study published, Reddy and colleagues from National Center for Food Safety and Technology looked at pressure-assisted thermal processing of various Clostridium botulinum spores, type A spores, and Clostridium sporogenes spores. And what you will see, for example, at 101 degrees Celsius, it had a D value about 14 minutes. Whereas if you repeat this experiment at 600 megapascal, 101 degrees Celsius, this acceleration of spore reduction under these conditions is only takes 6 minutes. If we repeat this at 117, it's going to become 0.33 and 0.35. So thermal become a dominant factor. Similar trend can be observed with the Clostridium sporogenes spores at 70 and 9.8 and 2.1 and 0.55 minutes. These are all for 1 log reduction. Look at the subsequent follow-up study by Skinner et al., where they looked at CAP9B, HAMB, 610F, Clostridium spores. So these are different spore crops or strains. And you can see here at 83 Celsius, at atmospheric conditions, one log reduction requires about 1.24 minutes. On the other hand, if you do it under 600 megapascal, it has about 6 minutes. So, in other words, pressure has a protective effect under these conditions. And when you increase the temperature to 91, it's 0.03 versus 1.34. And for Clostridium botulinum 610F, 83 1.56 minutes versus 9.3 minutes under pressure, and 91 Celsius zero point zero 0.07 versus 2.46 minutes. So this kind of shows that there are certain strains can have antagonistic relationship between pressure and temperature. Some strains can have, or most of the strains can have synergistic relationship with pressure and temperature. So this illustrates the importance of testing pressure temperature kinetics of wide range of bacterial strains. In another interesting study, um, Ruggier and colleagues looked at the survival of anaerobic bacteria, like particularly Clostridium botulinum, in coconut water. So they kind of conducted a couple of different studies. So they did the experiments at 4 degrees Celsius and 10 degrees Celsius without any pressure treatment, and with the pressure treatment, which is roughly 593 megapascal for 3 minutes at 4 degrees Celsius. And they also added about 2 logs of Clostridium botulinum in the um, unfiltered coconut water, and then they stored this up to 45 days. What we found is that this Clostridium botulinum levels remain unchanged and stable over 45 days of storage. On the other hand, the green line here, which is the non-HPP stored at 10 degrees Celsius, and HPP treated at again at 10 degrees Celsius, started growing. Total levels of anaerobic bacteria increased by day 45. But they did not notice any detection of Clostridium botulinum toxin. It appears that the antibacterial compounds in coconut water, such as lauric acid and antipeptides and so on, probably may provide some inhibitory effect on growth of toxin production under these conditions. And they repeated these experiments after filtering the coconut water under these conditions. What they found is kind of somewhat similar results, except the growth started occurring at 30 degrees and 45 degrees during storage. Thus, it is important to realize that when the food processors um, process low acid drinks, it's important to maintain and store them at 4 degrees Celsius or at max 10 degrees Celsius. If you start having a temperature abuse during distribution and handling about 10 degrees Celsius, you're likely to have potential growth, and potentially there may be some um, opportunity for outbreak. So this provides to the next thing. So there is also an interest to add natural antimicrobial compounds so that we can cut a couple of things. One, it can help to reduce the process severity, and they can also inhibit the bacterial growth during extended growth and storage. So for example, in this study, Deryagi and colleagues looked at PATP treatment of amyloliquefaction spores. They kind of roughly had about 4 log reduction under these conditions. This is done at 600 megapascal, 103 degree, 105 Celsius for 3 minutes. On the other hand, when they combine with this treatment with chitosan, they get some additional reduction, and chitosan liquors addition, they get much more reduction. This illustrates that by suitable combination of pressure, temperature, and natural antimicrobial compounds, it's possible to reduce the process severity. So at the moment, very limited studies looked at some of these type of effects, and we need more research so that we can able to understand how different natural microbial compounds can be combined in a synergistic way so that you can able to have a stable product. At the same time, you can also reduce the process severity. One of the limitations of the natural and microbial compounds is that they may lead to significant sensory changes in the product. So that's something you need to consider so that it doesn't affect the sensory properties of the food. So that's why more research is needed. I mentioned previously the high pressure processing is primarily batch process, but with the beverages, there's an interest in continuous treatment. So at Ohio State, we are looking at ultra shear technology. Basically, it's a continuous method of processing. It consists of you have a beverage product, and then it passed through a heat exchanger where initial temperature can be conditioned, then pressurized to 400 megapascal, and then it's depressurized through two valves, two homogenization valves, and then in between you have a whole tube, and then you're going to cool the product, and then it can be aseptically packaged. So we just started this project, and some of the preliminary results of this project is presented by uh, Zhu and colleagues in the poster P249, thermal pressure and shear on the inactivation of the Lactobacillus brevis and Bacillus cereus bacteria. And you are welcome to take a look at that post as well. And we plan to conduct more research in the coming years and will be sharing through various professional societies. So in summary, the food processors can benefit from use of non-thermal processing technologies such as high pressure processing. These are all tools to preserve the liquid foods with the fresh-like characteristics while minimizing the thermal impact. The risk associated with survival of bacterial spores after pressure pasteurization should be carefully considered, and the temperature conditions during handling and distribution needs to be carefully monitored. More kinetic studies are needed to understand the pressure thermokinetics destruction of various vegetative and spore forming bacteria in different food matrices at the function of pressure, temperature, and shear process needs to be considered. This will be helpful for the food process development. With that, I conclude my presentation. Um, I would be happy to address any questions through the chat mechanism available through the food protection meeting, or these are my contact details, and I would be happy to take a look and address any questions through email, phone, and you can also take a look at our website. I also like to acknowledge the contributions from USDA NIFA, food industry, and Ohio Experiment Station for various parts of our study. Thank you.